can hear you, but just the video is a bit stuttered.
Okay, it will be. I guess it gets better. I hope. Yeah. So you were saying something.
Yes, sir, I had a doubt in a few questions in the recent relief flow assignment.
Yeah. So we can get started with that. Yeah. You want to share your screen or something? You're on mobile.
Yeah,
You're on mobile.
no, I'm on laptop
Yeah,
now.
that's
Just give me a moment, actually.
great. So you just to show. Yeah, yeah.
Yeah,
Take your time. And I'll tell you if I am able to see your screen. Once I'm able to see the screen, I'll let you know.
so can you see the screen I'm sharing?
Yes, 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 yes.
So, this was the question from the rally flows, and no, sorry, not
Hmm.
rally flow, it was a generalized 1D flow. So, after rally
Okay.
flow. So,
Hmm.
this question was like, uh, just to give a gist of it, there there is a flow established in this tube. It is a constant area tube. So there are three sections marked. From section 1 to 2, it is a isentropic section. And 2 to 3, the 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 tube is getting heated, means the pipe is getting heated, and then from
Hmm.
3 to 1, it is being cooled. And at at section 3, the conditions are such that we get a mark number 1 at section 3, means it is maintained that way. And the maximum Mach number which the flow can attain is 2, in this flow.
Hmm.
So so now they had asked, uh, the question was, in what flow regime is the heated part and cooled part of the pipe would be respective. So there were options are like subsonic and supersonic and subsonic,
Hmm.
subsonic
Hmm.
and sonic and sonic.
Hmm.
Second and third and fourth are not possible. Fifth option says both A and B are possible. Subsonic, supersonic, and then supersonic, subsonic, respectively. So my question was, my thought process was like, if the flow is established, so if we consider the first case, subsonic and supersonic, in the heated region we get subsonic, and in the cooled region we get supersonic flow. So if we
Yes.
from the section 2, if we start with the subsonic Mach number, for example, say zero point 0.4, zero point 0.5. Now we accelerate, it gets heated, and it
Hmm.
accelerates to Mach 1. Then
Yes.
then it starts cooling. So now it transitions to supersonic
Hmm.
Mach numbers, and then it reaches section 1.
Yes.
Now it has to suffer a normal shock
Yes.
inside the pipe, so as to get the subsonic region inside the isentropic section, and also at the section 2, inside the again at the inlet. So it's like a cyclical flow. But in the option in so means the flow,
So
so the continuity is maintained.
why I said this normal shock was
Sorry, sir.
there are two shocks, one and two both. Is it?
Sorry, sir.
There are two shocks that would one and two. Is
No,
it?
no, no, no. At section, just before section one, it suffers a normal shock. The means
Pranav, you're able to
from
hear me out?
yeah, yeah.
Wait, I'll use my chat.
So my thought process from section 3 to 1 was like since since it will follow the same rally flow curve, the Mach number is increasing like from 1 to Mach 2. Uh, so when it is increasing along the rally flow line, the entropy should decrease eventually, and then when it goes on decreasing, it reaches a point, and after that point, it just suffers a normal shock.
So point one two at point one is
See,
it?
see,
At point
see
one.
your voice is cracking. Could you just type in the chat? You can read it. Yeah, yeah. At point one, there has to be a shock so that it transitions to subsonic flow just at the section one, and then since the area is not varying and section is isentropic, nothing the flow uh, the properties of the flow would be constant along the in this region. Then we get a subsonic flow at section 2 only, like that. That was my thought process. But contrary to this part, in the second option, it says that it starts supersonic in the heating region and then it goes subsonic. So applying the same thought process here. Now, uh, now it from when it goes from from supersonic to subsonic. Now it reaches to section one with the subsonic Mach number. But now there is no provision, or there is no way that it would accelerate to the subsonic Mach number, which it started with at the section two. So how can this option be possible? Yes, I cannot hear you. Oh, okay. Okay.
Hello. Yeah, you're able to hear me now, right? Great. So yeah, please go ahead. Sorry for this. So my internet is very bad, is it? Yeah, yeah, that's fine. I don't know what's wrong. My institute network went down for a while. Yes. Yeah. So the question is that the flow can be super subsonic and then supersonic if there is a normal shock at location. Hmm. Yes. Yes. Go ahead. Not this one. So this one. You can watch my screen. Great. You can also hear me through the this thing from a laptop also, is it? This one. This one. This is the question, right? Hello? Hello? I'm not able to hear you. Hello?
Hello.
Yeah, you're able to hear me now?
Yeah, now it's better.
Better. No need to call you, no? Yeah. So the
Yeah, yeah.
question is, okay.
So yeah, hello.
You call me. I'm not able to hear you. Hello?
Okay, okay.
Okay. Yeah. Yeah. Hello. So the mobile network is also bad, is it? Yeah, you can quickly say the question first. Yeah. Hmm. Yes. Hmm. Okay. Hmm. 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 Centropic section with a constant area. Uh, it's an isentropic section. So if it is supersonic, it goes to subsonic. If it cool down, so it's subsonic there. And then from subsonic, how can it reach supersonic conditions? A constant. Wait, let me see if these are marked wrong or anything. But there is a shock, is it? No, why the shock is up? Shock must happen. We just at the hmm. Okay, but does it say that there can be a shock anywhere? If a spark maximum Mach number of flow is 5 is 2. Ignore the transients. The temperature of the heated and cool section is melted some conditions. Okay, fine. This is question 1. For you, I guess for me it's question 1. So, okay, okay. So, what does it say? Like, then does not make sense, right? You can't have both. From 1 to 2, it will be subsonic, and then you can't reach constant area without supersonic flows. If you have a point from 1 to 3, the connecting edges are attached to a isentropic section. So nothing is changing. Yes. Then it means that it has to be subsonic and then supersonic. Yes. Let me think. A and B. Expansion data. Expansion data develops. Stay out. Indians constant like follow flow transition from supersonic to subsonic and vice versa is possible in direct flow. Electronic entropy is only. Okay, maybe they marked it from the thing perspective that uh, they're not considering the fact that this is a closed thing. If it is not closed, then that would make sense, right? Let's say this one and two is not closed. They are not connected by an asymptotic section. So the question essentially reduces to the fact that is there an isentropic mechanism to go from subsonic to supersonic regime, isn't it? With, right? Um, if you think about it, if you think about it, um, they also don't mention existence of a normal shock there, right? So you're saying the normal shock should exactly appear. Yes. Okay. Then- See, the problem, okay, suppose there is a normal shock at the exit of one, okay, right? So if that happens, there is a for entry of one, right? Just at one, right? So if even if that happens, no, across a normal shock, entropy won't remain same. Uh, hmm, yeah, but from let's say just before one, one minus and one plus. So at exactly one, there is a normal shock, isn't it? Let's say one minus one at one. What will happen? So you can okay, yeah. That the question B. How will the flow go from connect to supersonic if both options are correct? Let me. So there is a yes. Anyways, let me see. So the scenario. Let's talk about the scenario we are discussing. Okay. Okay. Suppose you are at some subsonic. Wait, where are we? Subsonic region. So this one. Let's say one minus. You're still able to see my screen, right? This is, let's say, one plus. So you say one plus is subsonic, right? This is two actually. Let me say this is two plus. Okay. Let me say this is two plus. Okay. Then this is three, right? At the sonic condition, this is three, right? So somewhere here, wherever the edge nose of this curve is, this will be three. I also draw an arrow for clarity. Trying to go on this. this part of it. Then we'll come back to ones. Till two to this, and this is 1 minus 1t. Okay. See, if you think about it, even your reasoning is wrong. If because you can't have this closed loop. Anyways, see, I'll tell you what I'm saying. Okay. So, now, see, this is 1 minus. What is that? So this is 1 minus, right? This is 1 minus. I'll tell you what I'm saying. So this is one minus, right? Just before this thing, it will be subsonic, isn't it? This is your argument, right? From subsonic, it goes to a supersonic thing, right? Now what you're forgetting is that and if there is a normal shock anywhere, if there is a normal shock anywhere, then this just after the normal shock, so there will be a 1 plus also, right? That 1 plus will throw this thing off to a higher entropy. Let me draw that. Maybe a but then 1 plus and 2 cannot be isentropic. If it throws it off somewhere like this, let me say, if it throws it off somewhere like this. See, the argument you're making is also not possible. That cannot be a normal shock. Okay, so you're saying, so it is somewhere like this, so that this happens. So that this happens somewhere here. So it throws it off at exactly 2 plus or just but yeah, see, my point is so you're saying 1 and 2 have is the exactly same point. Are they have the same entropy, but they will also have to be at the same point also. They can't be two different points. They have to be the same point. They should be the same point. This is the argument, right? Okay. But if we do it other way around, if we start from something else, yeah, this makes sense. This is completely fine if 1 plus and 2 plus are the same points. Um, that would be okay. Um, can that be? No, yeah. So this is okay. There cannot be any other way. It can't go from this thing, go to subsonic, and then yeah, you're right. This is fine. So this is the only argument. Great. Now I got it. Okay. Um, okay. So the maybe this question is not marked correctly. We'll have to write to them. Uh, but if you think about it, if we don't connect it, then this makes sense, right? See, the whole argument of this justification for this thing is that unlike fan of flow, there is a mechanism from going to subsonic to supersonic and so on. So it's not like fan of flow friction always pushes towards sonic conditions, but in rally flow, it's possible to have cooling and then moving away from sonic conditions. So that was I think that is the logic they're trying to just emphasize on. Yeah, then this does not make sense. Yes. Yes. I was thinking if there can also be a case where there is a normal shock, uh, can't be, no? Because, yes, sir. Acha, what if this is subsonic, this is supersonic, this goes to subsonic regimes, and we can't have anything to, okay, connected, and this is a constant area. Hmm. Yeah. No. When we say heating or cooling, so the question for the recorded session, the question is that if when we say heating or cooling, are we commenting on the total enthalpy or are we commenting on the temperature? So when we say heating and cooling, we mean energy balance, and in the energy balance, it's total enthalpy. It's not temperature, because as you know, the construct of temperature and heating breaks down when you have supersonic flows, isn't it? So if you heat it, sonic regimes, what happens? It cools down or what? I don't remember. Cools down. Somewhere it breaks down. Or it's subsonic regime only it breaks down. Yes. Yeah, there's a peak temperature. That is, yeah. But then this is the static temperature. That's fine. Yeah. Hmm. Right. Yes. Enthalpy. Yes. Which means that there has to be energy conservation. Okay, yeah, this has to be exactly equal. Yeah, that also has to be taken care of. Yeah. So you had another question. Another question. You don't. Okay. So let me go back to this thing. Yeah, I know this is a little flawed. Last assignment was also a little flawed in that sense. Second question, the last question we did. Yeah. Fine. So both A and B are possible. Okay. Maybe we'll have to write to them. Okay. Um. Fine. Okay. So I'll go back to this laptop screen recording. Okay. Okay. It flows itself. Try to solve a few problems, and then we'll jump to small perturbation theory or this method of characteristics. Let's look at this question. So air and you can go and have a read at this question. Does a constant area duct with Mach number of 1.6, temperature of 200 Kelvin, pressure is 0.56 bars. After some heat transfer, a normal shock occurs. Okay, whereupon the area is reduced. Okay, at the exit, the Mach number is found to be 1 and the pressure is 1.2 bar. Okay, compute the amount and direction of heat transfer. Okay. So this is supersonic. Supersonic flow is heated. So it will heat up to a lower Mach number. So M2 has to be found out. Then corresponding to M2, there will be a normal shock. So the thing goes to a subsonic regime. So M3 will be a subsonic number. And then there is a area reduction. Area is reduced. So a subsonic flow where area reduces is accelerated, so the Mach number increases to 1. So we know the sonic conditions are equivalent in at this duct, whatever this variable area duct is towards the end. And based on that, we'll start calculating. Okay. Uh, from 3 to 4, we also know that the flow is isentropic. So now, how do we start this question? Um, so another thing which is important here, the way to solve it is Mach number is 4. This is fine. Okay, so how do we solve it? Do we have enough relations to solve this thing? We know S3 equals to S4, and we know P4. I'm writing knowns and say knowns. S3 is known, P4 is known. It's also known that Mark 4 is 1. So what else is known? No. Just using this P4 thing, we can actually calculate stagnation quantities. So the total 4 is possible to be calculated. We don't know temperature there, so nothing else can be calculated. Okay. Um, because regions from 3 to 4 are isentropic. So just writing entropies, we can just simply write total pressures are same. What else? If we go on from the other end, we know T1, one is known, and by the virtue of this mark numbers, we know the total quantities also. So let me just write that. Things are known. Um, Now from 1 to 2, uh, well, these are knowns. Now let's write some relations. Relations. Uh, this will actually go in relations. So these are the relations that we know. And total temperature is also known because this is the okay. So now across the shock, we know that the total temperature remains constant. What else? So 1 to 2 are related by what? 1 to 2 are related by, they're not related by anything. Okay. Yeah, they are related by their sonic temperature. If we talk in that sense, they are related by, there is a T star, a sonic temperature. Let me write that. So T star corresponding to 1 is equals to T star of 2. Okay. 2, 3 is related by the normal shock thing that the total temperatures are the same. Um, 3 to 4 are related by the essence of this question is that normal shock does not disturb the sonic temperatures. That is the essence of solving this question. So this is the one relation that we will essentially need at some point, no matter how we solve this question. And so this is essentially saying that So the Mach number is 1.6. So let's take it's 1.6 or it's 1.60. Yeah, that's Mach number of 1.6. Yeah. See, 1.6 corresponds to we have a temp of 0.7014. Okay. So now with this entry, we know T star is actually T star by T1 by 0.07. Let's calculate that. It will be twice or something. Then drops. Not twice, sorry. Um, and the temperature is 200 kelvins. So T star comes out to be 285 kelvins. Okay, fine. Now, now we'll have to stop and trace back our steps from 4 to 3 first of all. So we know the if okay. So the way to do this thing is that for T star 3 there is a subsonic Mach number. Uh, wait. So on the this thing, okay, let's also find what is P star values also. Because you see, P star values will also be the same. So let's find out P star values also. So this now if I use this value, start by P1 and by something. Yeah, P5 and P56. Let me calculate that value for us. P star is 69. 696. This is bars. Now, let's note the fact that no matter if there is a normal shock, P star values is again not gonna change because the sonic conditions are gonna still remain the same. So now that we know the sonic conditions are 1 point, so this is a P star value. Wait, so now okay. Now we are going to use the fact that we're going to use this relation um, that P3 is P24. So first of all, let's find out what is P24, P24, P total 4. PT4. So let's find out what is PT4. So corresponding to that, this we will use isentropic table because we have a Mach number for it. In fact, it's not even a function of gamma. It's just sorry, it's not a function of Mach number. It's just a function of gamma. We don't even need anything else because we know Mach number is one there. Isentropic relations. What is the relation between P by P naught at Mach number of 1? It's 0.5283. Yes, that's a famous ratio. 0.5283. So 1 divided by 0.5283. What is that value? Let's find out what is this thing. 1.2 times. Divided by 0.5283 is 2.27 bar. Okay. Right. So PT3 is also 0.27 bar. See, what we can do now is find out. So one more thing that we can find out is P. So the logic here. So what are we trying to do here? So rather than me solving this problem, I just wanted to, for someone who has not solved a single problem in these Rayleigh flows, simple flows, just wanted to emphasize what is the approach, how are we thinking? Suppose if we are blank at some point of time, how do we approach this? So we start look for knowns and relations. So I started with writing knowns and relations, and I tried to use relations to increase our number of knowns. Okay. So one thing which I which I thought about was that we have at some point of time, because we know that there is a normal shock, we'll have to use the fact that there is a subsonic Mach number corresponding to a supersonic Mach number, which has the same ratios and so on, same sonic conditions and so on. So now that I know a total quantity behind the shock, total pressure quantity at behind the shock, and I know uh, uh, what do you say? A star quantity, a star static pressure. I know again behind the shock, I guess. Yes. So P star of 3 is also this. So this is P star. This will be equal to P star of 1 because they are all along the Rayleigh flows, along the same Rayleigh curve thing. So because of that, we know a star quantity. If we can get to know a ratio between P star and P, or P star by P total or something, then using these tables, suppose if I can get any of these ratios, then I can find out the Mach number which I and can then proceed. Once I just need one Mach number or something to proceed, right? And this has to happen at across the normal shock because we know something, some detail a little upstream of the normal shock and a little downstream of the normal shock. So that is the idea there. So now one thing which I thought about was if I know the total pressure at this quantity, I can calculate. Well, I can't calculate total pressure. I can calculate the total pressure, total sonic pressure. Again, sonic pressure also remains same. So we can calculate that. So if I do that, and then we can use this ratios. Rather than using this P star ratio, I can use P total star ratio. So if I do that, first of all, I have to find P total 1 for that matter of thing. So if you do that, what is P total of 1? First, let's calculate that. So Mach number is 1.6. So P by P total is a ratio of 0.2353. Let's use that. So this is P1 divided by 235. 353, yes. So now let me check what is this number. It's 2.379. 7. Okay. This is the total pressure there. Let P total star. Okay. This P total star there. Corresponding to the entry of this thing. This entry is 1.17. 0.1756. Total by 1.17. Let me just check if that is fine. 3756, I think. 6. Let us calculate what is P total star. See, up till now we have not used one known, which is P4. We have not used it. Uh, well, we have used it, but we are sitting idle with this thing. At P total at 2, but P total at 3 is 2.27. We can't proceed around it. So we are going from a different direction again, going back. This is something that you will have to, if you're in practice, then you can quickly do it. But if you're out of practice, if you're blank, suddenly blank in the exam, then you can proceed in this, you can think in this manner so that you can try to solve the same, a difficult problem or something. So, so P total star we'll calculate is 2.23799 divided by 1.1756 gives you 2.02 bars. And now we can use, now we know P3 star. Okay. So we know P star total. How much? 2.0244. So now we can calculate this ratio, right? So, and then we will identify a entry, a subsonic entry corresponding to this ratio. That is how we solve this problem. So this ratio, actually we need to find a ratio of P total by P total star. So 1 to 1. Okay, so now let's go for a scrutiny of the tables, teleflow tables. Subsonic value, which gives you a P total by P total star of 1.12. Okay. So we see we are somewhere near 1.1. So something close to 0.66. So mark of close to 0.66. Okay. So now we know mark number of point at 3 is 0.66. So let me just once check if this is the right thing. No, wait. Oh, it was 1 point. Okay, so slightly similar value. P total is 2.38, is it? 2.38, fine. Couple of things are okay. This one is okay. Yeah. So here you see we wrote down relations in total sonic temperatures, but you see the pressures are also similar in this problem. We use the temperature quantities to solve for it. So now corresponding to a value of close to 0.121. So we are getting a value close to 1 to 1, right? And that value is 0.58 or something close to zero point 0.6, right? 1 to 1. So I'll just assume mark number is 0.6. Now we'll go. So let me write this down. Get 0.3 is 0.6, let's say. We can do it more accurately. Try to interpolate and see what value it is. The mark 2 is something that we will get from here, from normal chocolate. Now we'll have to either find a supersonic entry similar to P naught by P naught. Well, no, not that way. So we'll have to go to normal shock tables. There is no other way. Go to a normal shock table and look for an entry of 0.6. Suppose entry I get is 1.84. So I'll use that right now is 1.84. You see how heating has accelerated the flow towards it. So now we know that Mach number is 1.84. So this is acceleration. If it would be heating, the flow would have gone away from, would have gotten closer to sonic conditions. But now that we see that the flow has gone away from sonic conditions, we know this is cooling. How do we calculate the heat transfer? So we know the direction of heat transfer. How do we calculate the amount of heat transfer? Nothing. We know the total temperatures. We'll subtract that and find out the heat transfer, Cp delta T. So Q is always Cp, as he asked, Pranav also asked in the starting of the lecture. It is Cp delta T total. You can think of Q as like that. Wait. So yeah, that's fine. Now, so we have to find total temperatures corresponding to both of these quantities. Um, we know Mach number of just upstream of the shock, the Mach number is 1.84. We also need to find temperature conditions there to find out the total temperature. But we have is yeah. So there is one more step that we need to do. Let me copy paste this slide to make a note. Let's make some room. Yeah, remove this question to make some. Okay. Mm, Fact. So how do we do this? Again, using the fact that 1 and 2 lie on the same Rayleigh flow, so they have the same star quantities. Um, we can actually find the total pressure ratio between P total of 3 to P total of uh, 2. So we know P total of 3 is 2.27. Using the normal shock tables, we find out the P total of 2. So let's do that also. Normal shock tables, 1.84 was the Mach number. The total pressure ratios are 0.795. 0.795. So we use this. So now so you have to use multiple tables while solving this problem, and there are multiple flow features in the same problem. You have to use the same different tables. So the total uh, T by the total of T is 0.9795. Let me just check. 0.795. Yes. Um, so we can find out what is P total to. Is ought to be equal to 2.27 divided by 0.795. 3.855 bars. Now, the total pressure, this thing also, total pressure, which is 2.0244. Should get the same this thing. I did this redundant, but let's check. That would be a good query. Let's check this if we are going to sanity check. Point 855 divided by 2.0244. It's 1.41. Let's check if this is the ratio we get corresponding to Mach of 1.84. Rayleigh flow tables. So 1.84. So we get a total pressure ratio of 1.48. And we should have gotten somewhere close to 1.4, somewhere something lesser than 1.84, because we have taken some broad, just the most closest entries. We are getting this discrepancy. And that error is also not very large, 1.48 and 1.41. The error in second decimal, not even the first decimal. So again, some amount of error. But anyways, this was the sanity check. Let me think, how do we find the temperature there? So we know T star values. We can find out. Wait, what else do we know? We know T star values. So we can find out T2 also, right? T2. Yes. So we can find out from this table 1.84. We could have directly looked for this T star by T value. It was not required to calculate P naught there. But anyways, 1.8, we stick to 1.84 entry, 0.7155. 0.7155. Let me check what is Mach 2 once. Hey, no man, Mach 2 should not be 2.6. Anyways, uh, so that entry for T star is 0.7155. 0.7155. Or let's look at the total temperature entry only. Why to look at different entry? Okay, this is fan of entry is 1.84. Point eight 0.8273 T naught by T naught star. So T2, T total 2 will be equal to 84 T equal to T only, no? 78 to 17 times 285 or 285. I haven't calculated T total star. We have to calculate T total star also. Let me do that. So this is going to take it for 1. This is the ratio that we want to use now, and times T total 1. T total 1 we found out, haven't we? Or we can just calculate. Let's calculate T total 1. 200 Kelvin times 1 plus 0.2 times 1.6 square, 302.4 Kelvins. And this ratio is 1 divided by 0.884142. So this, if I look into this thing, I'm going to get is 0.884142, 282, 282.93. Yes. And the total temperature of T total 1 was 302. So T total was 302.5 kelvins. And just multiplying Cp and Cv, you will get a heat transfer value. So this is how you solve this problem. The exact answers, do I have the exact answers? Yeah, so I don't have the exact answers, but the process, let's look at the process, what's going on. So from 1 to 2, it was supersonic, so it went away because we were cooling it. And then the normal shock happened. So 2 to 3, And then because of variable area type, there's a compression. Is it expansion? Is it? Yeah. So it goes from a low Mach number value to it increases. So variable area duct. So area must increase, but area is reduced, isn't it? Area is reduced, so velocities will increase. Fine, 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 fine. So it has been expanded because it has been expanded by increasing the velocities, by decreasing the area flow path it follows. Okay, fine. Let's look at probably I'll start the small perturbation thing. Or should we look at this? No, no, this one not one look at it. Need to move this. Okay, 170 Kelvin, points on water secondly. Transfer takes place in the Today the internet is very bad. So what happens? I think it is better now. I'll keep my screen, this camera shut off so that bandwidth it can work with the poor bandwidth. So as I was saying, let's solve this problem. There are two things given to us. We have a duct from 1 to 2 where heat is being exchanged, and the flow enters at a Mach number of 2. The temperature and pressure conditions are given at the entry. And then post the heat transfer, there is a converging section. Again, the flow will expand. Flow will expand. And the exit Mach number is 1. So again, sonic conditions at the exit of the setup. Assume the inlet and the inlet condition exit Mach number remains fixed. Find out the amount and direction of heater. Similar problem, very similar to what we had done. Again, knowns and unknowns. We know area ratio. First of all, let's use that. If we know the area ratio, uh, we know the Mach number at 2, right? And with the fact that this area ratio is a sonic area ratio. So A3 is in fact, oh, should not write it there. So A3 is in fact equal to A2 star, if you think about it. Uh, so 2 is characterized by area ratio. So let's use this area ratio to find out the Mach number is exit at the exit of the duct. So isentropic relations again, area ratio of 1.45. We need to find a sonic flow. So at 2, we expect the flow to be still uh, supersonic. It can't reach a Mach number of less than 1. Okay, so it's is it given to us? Q is a constant. Let's assume that the Q is not varying in space. So it's not like we're heating and cooling or doing some funny businesses, heating in certain section and then cooling in certain section. So then we can assume that if there is a supersonic flow, it will remain supersonic. Uh, uh, so it will be a supersonic flow, but lesser than probably lesser or hot. Let's check based on the area ratio. We'll get to know if it's uh, heating or cooling. So our area ratio of this thing will give you the Mach number at 2. So if you look at it, area ratio of 1.45, something close to 1.81. So Mach number is close to 1.81. So M2 now with that, if M2 is 1.81, we know that there is a process of this is a process of heating, and then we can simply again by using the same strategy we can find out the heat transfer. The first we have to find out the total temperature corresponding to T1, then the let's say sonic temperature corresponding to the Rayleigh flows. We'll use that with this Mach number value to find out the total temperature at 2. Subtract the 2, multiply by Cp, and we'll get the amount of heat transfer. That is when there are no shocks. But the question hints if there is a normal shock somewhere, we know that from supersonic regime it will go to subsonic regime. So now we need to find the area ratio corresponding to subsonic, a subsonic Mach number. If we do that, the Mach number corresponding to 1.45 will be somewhere close to a 0.45, right? 0.45 itself. So in the B part, on the B again, 0.45. And now, if you have Mach number of 0.45, then what? Then again, nothing across the shock. So now we'll have to take care of. There is a shock somewhere. Okay. Okay, fine. Then there will be a shock. Let's look at the C part and then we'll solve for B. For part B, does it make any difference where the shock occurs? Which is a good question because essentially we should, in order to solve B, we need to worry about where the shock occurs, and then we'll have to calculate two heat transfer values, two heat amount of heat transfer values, one before the shock and one after the shock. Add them and then get the answer. But then C part forces us to speculate that is it the case that the sum is a constant and it does not matter where the shock appears. So let's look at it. Why will the shock location of the shock will depend or will not depend? Let's try to reason that. For that, we'll have to go here and suppose that we are somewhere. Let's say we are somewhere here and we don't know the exact location of 2. Okay, so we are somewhere at 0. Finally, finally, the way we do this is now initially we had and the final value will be some Mach number. So let's say this. Final is F. So now note that both F and 0 again have the same sonic conditions, which implies that the initial and the final temperatures are the same. They are not the same, they're fixed because Mach numbers get fixed. Mach number at 1 is fixed, Mach number at 2 is fixed. So because there's a change in internal energy, Q is Cp delta T, and these are state properties. So it will not matter where the shock occurs. Shock can occur anywhere, but that won't change the state properties at the exit or the inlet, because we know that what makes sure that the change in the location of the shock does not affect the state properties. That governs from the fact that this is the solid conditions at exit, and there is an area ratio in the converging section of the duct. So now, because of that, no matter where the shock occurs, it is essentially Cp delta T being state properties. It will not matter where the shock occurs. We can just simply calculate these values. We get two values. Uh, can we know which will be higher or which will be lower? Is that possible? If I think about it, and also another reason, no, the location of the shock does not matter is across the shock, the total temperature remains constant. So essentially, no matter where you go, the well, that is not a good reason behind independence of the shock location on the total heat transfer. Let's leave that argument. Anyways, going back to what I was saying, can we compare without directly solving for the uh, two values? Can we tell which will be higher and which will be lower? Can we do that? So what is this? Well, it all depends on the total temperature values, isn't it? In this section, if I think about it, amount of heat transfer. Okay, so if I open that book, let me open that book. Look at the Gasdynamics. So 77, 0 to 77. Yeah. So earlier we were in supersonic regime, and we knew there will be this thing. Uh, there will be some heat transfer, but then this one goes to a lower value, and then it increases this value along this value. Probably we can't find out. So I was thinking graphically, is it possible to comment on amount of comparing if there is a shock or if there is not a shock? Can we compare the amount of heat transfers? But probably not. Why? Because suppose it's the supersonic conditions and they are same area ratio. These 2 points, are they related on an isentropic table? Or saying on the isentropic table, are the same area ratios uh, related? Are they? Mhm. Related, right? They neither have the same stagnation ratios or anything. Yeah, they're not related at all. Yeah, they're related by. They're not even related by anything. Are they related by a shock relation? Maybe they are related by shocks. So Pranav, are you there? Let's discuss this. This is an interesting thing. I'm not sure. Are you there?
Yes, I am.
So, do you were you looking at what I was like what I was asking or what I was trying to figure out? My question was so the originally the question was this was the problem we were trying to solve, and in this problem, we without going ahead and figuring out the values of the heat transfer, I wanted to understand if we can find out the heat transfer in part A will be higher or lower than heat transfer in B. And for that, we wanted to see because if there is a normal shock somewhere, we will have a subsonic Mach number at 2 in B, whereas a supersonic Mach number in A. I wanted to know if those two conditions are somehow related. So these two conditions are found out on the isentropic table with the same area ratio entry. But for a given area ratio entries, the subsonic value and the supersonic value, are they related? Are they related by the normal shock tables? I think, isn't it? In a variable area duct, um, A star values across a normal shock. So if I open that thing, so do you have any comments to make there?
Uh, um, I don't have any comments right now.
Do you
Like,
know the answer to this?
just give me a moment. Think.
Yet, no? You're thinking?
Yeah.
Hmm. The question is this one. this conditions here and conditions here, do they have the same area ratio? No, right? But they don't have the same total pressure, but the total temperatures are the same. Okay. Um, got it. They're not related. Acha, tell me one thing. If I draw a straight line here, if it's a totally, this is all subsonic, right?
Huh?
Suppose, go ahead. Saying
No,
something.
no, no, no. What were you saying? Subsonic?
I was thinking, my question was across a normal shock. See, we are seeing a trend that across Fano flows and across Rayleigh flows, normal shock does not change the star conditions. Is that true for even for variable area flows? That I don't know. It is not. It is not. Okay, it
No,
is not
yeah, means it's not because the
because
period changes.
but P star values. Do P star values also change? Okay, I think I got it, but we can discuss this if you want to. Let me tell me if my reasoning is fine. Across a normal shock, A star is a constant, isn't it? Are you aware with this equality
Yeah.
across a so also the fact that across a normal shock, A is also a constant, right? Area does not change across a normal shock, which implies that P total 1 right T total 2. So actually they are related somehow. Wait, let's see. So P total 1 by P total 2 will be A star 1, A star 2 by A star 1. And so their area ratios A by A star. Let me use this. A by A star value B. This value will be what? P total by. Again, P total 1 by P total 2. This is fine, right?
Yes, yes.
Which means that across a normal shock, A by A star values, A by A star values will it decrease or what will happen? It will increase, isn't it? If A by A star is the ratio we are looking at. Otherwise, in isentropic tables, is it A by A star or is it A star by A? A by A star. So this is fine. So A by A star values will decrease, yes, across a shock. So even there, numbers of constant A by A star values are not even related by isentropic, this normal shock relations. Fine. So we can't comment on what heat transfer will it be higher or lower, isn't it? Or can we? by any other logic. Here, if suppose this is our inlet conditions, there can be two things that can happen. It can go to a subsonic value, the final one, or it could go somewhere midway. Then this normal shock total enthalpy remains constant. Okay, and then again heated. Yeah, maybe we can use this. Wait. Let me redraw it. Yeah, then this implies that if it is subsonic, then it will be higher, no? Yeah, we can relate them. So if this is initial, it goes, there is one way to, this is the supersonic way, this is the simple way. What if we do it this way? So across a normal shock, and trees are gonna remain same, and area ratio, but then it depends, no? Where do you stop? This is there. Yeah. So it could be either way. It could be, it does not depend. Is it? Yeah, it depends. It depends. It we can't say. It depends, right? There.
Will depend where the normal shock happen.
Well, no, it does not depend where the normal shock happens. It depends where what is the final Mach number. Normal shock happens because of the pressure ratios. Heat transfer is happening uh, because of the total temperatures at the inlet and the exit. Yeah, and these are two independent quantities. There can be no normal shock and still, yeah, fine. So they are not related. We'll have to calculate. There is no relation between these two bad questions. Probably, like as far as we could see, these two won't depend on each other. Like they don't have any relations. Uh, Fine, that is okay. I think it's 7:48 already. I'll stop today. Plan was a little bit something else. So I'll tell you what the plan was. I didn't want to cover this part of it today. I wanted to leave it for the next class. And I was looking at something of this method of characteristics. I'll open that. Something that you must have looked at in the initial units. I was trying to simulate it. Just see in the video lectures, a recipe is given. I wanted to apply the recipe in one lecture, see how it goes. So I was able to go up till this step. I just need to move one more step and draw the nozzle contours also. That is one last step, and then we'll be able to this method of we can see how that method of characteristics work. But somewhere I'm getting an error as well. So that also have to figure out. So next class we'll do it. We'll do this and maybe some small problems on small perturbation problems. Maybe revise of all of it, and then probably the next class will be the last class. So yeah, so we can stop today. See you next time.
Thank you.